Hey everyone, welcome to this explainer. Ever just look at your watch, buy a coffee, or punch a number into your phone and think, how did we actually agree on how to write these down? It's a universal human problem, right? How do we keep track of things? Today, we're taking a focused journey into the cultural evolution of place value. We are going to decode the brilliant, ancient number systems that laid the very foundation for the math we use every single day.
Okay, here's our roadmap for today. We'll uncover a secret number treasure, explore the Mesopotamian base 60 system, look at Mayan base 20 math, decode Chinese rod numerals, and finish up with the Indian number system. Let's get right into it.
Section 1. A secret number treasure.
So, we're going to kick things off with a story about a young girl named Rima, a super old book and a secret language of quantities. It begs the question, right? Since when have humans actually been counting? Like, before we had the digits 0 through 9 staring back at us from our keyboards, how did early humans wrap their heads around quantity? In our source text, Rima is flipping through an old book when suddenly, a piece of paper covered in these weird symbols just falls out. Her dad takes one look and drops a bombshell. These aren't just random scribbles. No, this is literally a 4,000-year-old numerical language from Mesopotamia, around modern-day Iraq. Just imagine holding a piece of paper and realizing you're looking at math from 4 millennia ago. Wild, right? Now, this kind of makes you wonder why these systems were invented in the first place. Well, the primal need to count goes all the way back to the Stone Age. These early humans, they weren't sitting around doing calculus. They were trying to survive. They had to track their food, count livestock, handle early trade. They even had to track time, predicting full moons and the onset of the seasons so they could actually grow crops. But obviously, they didn't write down a modern 10 or 20. They had to engineer their very own symbols from scratch.
Okay, so here's the crucial thing to understand. The ancient Egyptians didn't have digits like 0 through 9 like we do. Instead, they built everything around what we call landmark numbers. Imagine you're trying to count a massive pile of stones. Instead of counting one by one forever, which would take a lifetime, you group them, right? You make groups of 10, and then you bundle those into groups of 100. These group sizes, 1, 10, 100, are your landmarks. And the Egyptians used these exact landmark numbers to systematically build literally any value they needed.
Now, instead of the abstract squiggles we use today, the Egyptians used a brilliantly visual system. They drew hieroglyphs straight from their daily lives. Notice how they used a simple vertical stroke for the ones. For the tens, they used an arch. It kind of looks like a cattle hobble. And for the hundreds, they drew this beautiful spiral representing a coiled rope. To write a number, you just stacked up the right amount of strokes, arches, and coils. It's incredibly visual and, honestly, instantly intuitive. Adding in this system is surprisingly tactile. To add two numbers together, you just follow 3 really simple steps. First, you toss all the symbols from both starting numbers together into one big pile. Second, you group the identical ones together. So, strokes with strokes, arches with arches. And finally, you simply trade them up. Every single time you hit a group of 10 identical symbols, you swap them out for one of the next landmark symbol. 10 strokes become an arch. 10 arches become a coil of rope. Seeing this addition play out is just so cool. You bring your individual strokes and arches together visually before simplifying, and it just makes perfect sense. Say your addition leaves you with 15 strokes. Well, you wouldn't just leave them sitting there. You grab 10 of those strokes, bundle them together, and replace them with a single arch, leaving just the 5 remaining strokes behind. It's exactly like taking 10 single-dollar bills to the bank and trading them in for a $10 bill.
If we take a theoretical base 5 system and compare it to a base 10 system, we see something amazing. Landmark numbers aren't just random choices somebody made up. They are sequential powers of the base. In the base 10 system the Egyptians used, your landmarks are 10 to the power of 0, which is 1, 10 to the power of 1, which is 10, 10 squared, which is 100, and it just keeps going. This hidden mathematical structure makes computation almost magical because it gives you this perfectly predictable, unshakable ladder to climb, no matter how high you count.
At first glance, drawing a coil of rope seems worlds apart from the digits we punch into our phones today, right? But look at the underlying mechanics. In Egyptian addition, you physically draw the symbols, group 10 of them, and trade them up. In our Hindu decimal addition, when a column hits 10 or more, we carry a 1 over to the next place value column. While they look completely radically different on paper, both systems share the exact same logical DNA. Reach 10 and carry over.
Having a base system is an absolute game changer. It gives us efficient number representation, meaning we aren't just forced to scratch infinite tally marks into a rock forever. It gives us beautifully simple rules for addition, but perhaps the craziest part, It makes multiplication a total breeze. In this system, multiplying by the base of 10 simply shifts a symbol to the next landmark. Multiplying an arch by 10 instantly morphs it into a coil of rope. Multiplying a stroke by 10, boom, it's an arch. The logic is totally flawless.
Now, I want you to think about this practically for a second. The Egyptians built monumental pyramids. They managed vast empires. So what on earth happens when an architect or a tax collector needs to write down a number like, say, 10 million? In a system where every single new power of 10 needs a totally unique drawing, a stroke, an arch, a coil, a lotus flower, what happens when those numbers get astronomically large? And there it is, the fatal flaw. Because they didn't have a positional place value system and they didn't have a symbol for zero, they were forced into a corner where they had to invent new symbols forever. Imagine having to memorize 1,000 different hieroglyphs just to do advanced math. It just doesn't scale. And it perfectly highlights why the later invention of the place value system and the number zero were such monumental leaps forward for human history.
All right, grab your mental styluses, it's quiz time. Let's start with representing modern numbers using these ancient landmarks. Picture this in your mind's eye. Question 1, how would you draw the number 324? And question 2, how would you represent 1111? Think about the specific landmarks you're going to need.
Let's see how you did. For 324, you need 3 hundreds, 2 tens, and 4 ones. So that's 3 coils of rope, 2 arches, and 4 vertical strokes. Simple enough. And for 1111? It is beautifully elegant. You just draw one of every symbol up to the thousands. 1 lotus flower for 1,000, 1 coil for 100, 1 arch for 10, and 1 stroke for the 1.
Okay, moving on to operations, let's see if you can actually calculate like a scribe. Question 3. Try adding 15 strokes and 15 strokes in your head, making sure to use the regrouping rules. And question 4. Try multiplying a single coil of rope, which represents 100, by the base of 10.
And here are the answers. So, 15 strokes plus 15 strokes equals 30 strokes, right? But wait, you wouldn't just leave a massive pile of 30 strokes on the page. You simplify that by trading every 10 strokes for an arch. So your final clean answer is simply 3 arches. For question 4, multiplying a coil by 10 bumps it up exactly 1 power. It immediately shifts to the very next landmark, meaning your answer is a single lotus flower representing 1,000.
Okay, for our 5th and final question, let's look at a bit of theory. Is it mathematically legal, within this specific system, to draw 10 coils of rope right next to each other to represent 1,000?
The answer is a massive no. The absolute golden rule of this base system is that the exact second you hit 10 of any item, you must trade them in. 10 coils of rope automatically convert into 1 lotus flower. It keeps the representations as concise and efficient as physically possible.
So everything we've looked at today, from the sandy banks of ancient Egypt to the core logic powering the laptop or phone you're using right now, is anchored by this single magical number, 10. It completely dictates when we carry over, when we group, and how we scale. And honestly, this base was almost certainly inspired by the very simple biological fact that we happen to have 10 fingers to count on.
To Section 2, the Mesopotamian Base 60 system.
Let's just kick things off with a question. Have you ever looked at your watch and wondered, why on earth does a minute have exactly 60 seconds and an hour has 60 minutes? Why not 10 or 100, like we use for literally almost everything else in our lives? Well, to figure that out, we actually have to travel back thousands of years. Take a look at this. This is an ancient clay tablet from Mesopotamia, basically modern-day rock. And yeah, at first glance, it kind of just looks like a bunch of random scratches, right? Just mysterious little cuneiform symbols pressed into wet clay. It looks like total gibberish. But what you are actually seeing is a highly advanced mathematical document. And today, we are going to crack this exact code together. They eventually develop what we call a base 60 or sexagesimal number system. Now, we use a base 10 system today, right? We group things by tens. But for these guys, their landmark numbers were the powers of 60. And yes, this is exactly where your 60-second minute and your 60-minute hour come from. It's wild to think about, but the influence of this ancient system is literally ticking away on your wrist right now. What is so brilliant about this is just how simple it is. To write down all these complex numbers, they really only used 2 basic marks, made by pressing a little stylus into wet clay. A simple vertical, downward-pointing wedge represents the number 1, and a sideways, angled symbol represents the number 10. And that's it. By just combining these wedges and angles, they could count all the way up to 59. But the real question is, what on earth happens when they hit 60? Let's see how this incredible conceptual leap works. Instead of just inventing some new complicated symbol for 60 or 3,600, they use the exact same wedge and angle symbols, but they change their position. Reading right to left, the rightmost group of symbols shows your ones. Move one spot to the left, and that group shows your 60s. Move left again, and that shows your 3,600s. The position of the symbol completely dictates its value. Let's compare that to our modern system, just to make sure it's clicking. In our modern base 10 system, our columns from right to left are ones, tens, hundreds, thousands, and so on. We multiply by 10 every time we jump to the left. But in the Mesopotamian base 60 system, those columns from right to left are the ones, the 60s, and the 3,600s, because, 60 times 60. This is a place value system, and it was an absolute game changer because it let them write an infinite sequence of numbers using just two simple symbols. Here's our first real-world translation. Imagine you're an ancient scribe logging a big grain trade. How do we write the number 63 using this system? Think about those columns for a second. We just have to break the math down logically. First up, how many 60s fit into 63? Well, just one. So step 1 is 1 times 60. Then what's our remainder? 3. So step 2 is just adding 3 ones. And here's how that actually translates to clay. We drop one vertical wedge in that left column, the 60s position. Then we leave a little physical space and we put 3 vertical wedges over in the right column, the ones position. 160 plus 3 ones equals 63. Boom! You just translated your first ancient clay tablet. All right, let's ramp it up a bit. Code-breaking example 2. How do we write 132? Same process. We isolate the 60s first. How many full 60s go into 132? 2, right? Because 2 times 60 is 120. That leaves us with a remainder of 12. So how do we build a 12 from our toolkit? We just grab one of those angled 10 symbols and 2 vertical 1 symbols. Look at how elegant this is. In the left column, the 60s column, you've got 2 downward wedges, then a gap. Then in the ones column on the right, you have 1 sideways angle for the 10 right next to 2 downward wedges for the 2. 2 60s, a 10, and a 2. 132. It is incredibly logical once you see the pattern, right? Pop quiz time. Let's lock in everything we've learned. How would a Mesopotamian scribe write the number 200? I'll give you a second. Really think about those columns. How many full 60s fit into 200? And what's left over? All right, let's see how you did. Step 1. 3 60s fit into 200, which gets us to 180. So that's 3 vertical wedges in the left-hand 60s column. What's our remainder from 200? Exactly 20. Step 2. We represent 20 using 2 of those angled 10 symbols in the right-hand ones column. 3 60s and 2 10s. If you nailed that, congratulations, you're officially qualified to be a Bronze Age accountant. But before we wrap up, we have to talk about a massive, glaring flaw in this system. The Mesopotamians had this genius place value system, but they didn't have a symbol for 0. If a column was empty, they literally just left a blank space. Now, think about human handwriting. It's messy. Getting consistent spacing in wet clay is tough. So think about the number 60. That's 1 wedge in the 60s column and a blank space for the ones. Now think about 3,600. 1 wedge in the 3,600s column, a blank space for the 60s, and a blank space for the ones. Without a 0, 1, 60, and 3,600 could easily all just look like a single identical wedge on a tablet. It created massive ambiguity. Which brings me to a final, slightly mind-bending puzzle for you. Knowing the rules we just learned, and knowing this terrifying flaw about blank spaces, how do you think a scribe would represent the number 3605? Think about it. That's 1 3600, absolutely 0 60s, and 5 ones. How huge of a physical space would you have to leave in the middle to make sure nobody misread it? Grab a pen, try drawing out the wedges and the gaps yourself.
All right, Section 3, Mayan Base 20 Math.
Imagine you stumble upon an ancient stone tablet, and it's carved with these mysterious dots, horizontal lines, and symbols that look kind of like little shells. Now, to the untrained eye, it's just art. But to us, by the end of this session, it's going to be perfectly readable mathematics. We're going to completely decipher the fascinating and highly advanced number system of the ancient Mayan civilization.
To really appreciate this code, we got to jump back to Central America.
somewhere between the 3rd and 10th centuries CE. Check out this quote. Among their intellectual achievements stands their place value system designed independently of those in Asia. That word, independently, is absolutely huge. They didn't borrow this math from anyone else. They engineered this entire place value notation system from scratch, literally separated by oceans from the mathematical developments going on in Asia and the Middle East. They were total pioneers.
So, while we use 10 distinct digits in our modern system, the Mayans, they used just 3 primary symbols. It's elegantly simple. For the number 1, they just used a dot. If they wanted 2, 3, or 4, they just drew that many dots. But once they hit 5, instead of drawing 5 dots, they used a single horizontal bar. So a 7, for example, is just 1 bar and 2 dots. Pretty straightforward, right? But the real game changer is this 3rd symbol.
Take a look at this beautifully stylized seashell. This is the Mayan symbol for 0. And honestly, having a placeholder symbol for 0 is considered one of the most massive advancements in the entire history of mathematics. Without a 0, place value systems just completely fall apart and complex calculations become nearly impossible. The Mayans figured this out centuries before it was a standard in the West.
So the math we use every day, the Hindu-Arabic system, is a base 10 system. Our landmark numbers are powers of 10, ones, tens, hundreds, and we write them horizontally from left to right. The Mayans did things entirely differently. They used a modified base 20 system, meaning they counted in groups of 20 instead of 10. And instead of writing side to side, they stacked their numbers vertically. You actually read them from the bottom up.
Let's build a number from the ground floor up. The lowest set of symbols represents the ones place. The tier right above that, the 20s. But look closely at step 3. The tier above the 20s isn't the 400s like you might expect in a pure base 20 system. It's the 360s place. That is exactly what makes it a modified base 20 system, and it's a wildly fascinating quirk we're going to come back to later.
Let's crack a 2-tier number together. How would the Mayans write 77? I'll give you a second to think. Remember, you have to break 77 down into groups of 20 for that top tier, and whatever is left over drops down to the ones tier at the bottom.
Okay, so here's the math. In the top position, representing the 20s, we need 3 of them, because 3 times 20 is 60. To write a 3, they'd carve 3 dots. That leaves a remainder of 17. So down in the bottom ones place, we need to write 17. How do we do that? 3 bars to make 15 plus 2 dots. Boom. 3 20s stacked on top of 17 ones gives us exactly 77.
Let's step it up a bit. How do you write 100? Think about it. 100 divides perfectly by 20. There are 0 leftovers. So what on earth goes in that bottom tier?
This is exactly where the magic of their 0 comes into play. To get 100, we put a 5 in the top 20s position. 5 times 20 is 100 flat, so that's one single horizontal bar up top. But we absolutely cannot leave the bottom tier empty, otherwise someone might just mistake our 100 for a 5, right? So in that bottom ones position, we drop in the seashell symbol. 1 bar stacked over a seashell equals 100.
Now for the 3-tier challenge. How do we decode 361? This is finally big enough that we get to use that mysterious 3rd tier, the 360s place.
All right, to build 361, we just need one group of 360. So a single dot goes in the very top position. That leaves us with a value of just 1 left over, which means we have 0 20s, so the seashell 0 goes in the middle position. Finally, we need a 1 at the bottom, so we draw another single dot. A dot over a shell over a dot. 361. The positional logic is just so cool.
Okay, this is your final test. Can you figure out how to represent 721 using the Mayan system? Seriously, I encourage you to pause this explainer right now, grab some paper, and calculate how many 360s, how many 20s, and how many 1s fit into 721.
All right, let's walk through it together out loud. Step 1, we start with our biggest landmark number, 360. How many of those fit into 721? 2 of them, which gets us to 720. So the top tier needs a 2. Step 2, what's our remainder? 721 minus 720 leaves exactly 1. Moving to step 3, since we only have 1 left, we need 0 20s in the middle tier. And step 4, we just need exactly 1 1 for the bottom tier.
So the whole shebang stacked together looks like this. Top position, 2 dots to represent 2 360s, making 720. Middle position, the beautiful seashell placeholder for 0 20s, and the bottom position, a single dot to represent 1 1.
Add them all up, and you have perfectly cracked the code for 721. If you got that, you are officially an archaeological codebreaker.
But before we completely wrap up this explainer, we have to talk about a pretty fascinating quirk, maybe even a flaw in their design. As genius as this system was, that anomalous third tier, jumping to 360 instead of a perfect 400, actually threw a major wrench in things. In a pure mathematical base system like our base 10, multiplication and complex arithmetic follow strict repeatable patterns. But because the Mayan system broke its own base 20 rule right there at the third level, doing complex arithmetic was actually notoriously clunky for them.
Which leaves us with this incredible historical mystery. If a pure base 20 system would have made computation so much easier, why on earth did these brilliant mathematicians deliberately choose 360 for their third tier instead of 400? Well, scholars think the answer is actually written in the stars. The Mayans were obsessive astronomers, and their solar year consisted of roughly 360 days. Did they literally warp their mathematical reality just so their numbers would perfectly sync up with their sacred calendar? It's a tantalizing question, and it really shows how deeply culture and science were intertwined back then.
Oh, and fun fact, remnants of this base 20 system are actually still floating around in the number names of some European languages today.
Moving on to Section 4, Chinese Rod Numerals. So, to really wrap our heads around ancient Chinese math, we got to realize they actually used two totally distinct number systems. You had your standard written system, for recording things in texts and documents, but for the actual heavy lifting, like the complex computations, they created this unbelievably efficient physical system using rods. This rod-based system goes all the way back to at least the 3rd century AD, and it was so good, they kept using it straight through to the 17th century. And honestly, the coolest part for us, it runs on a base 10 decimal structure, exactly like the numbers we use every single day.
Now we journey to ancient China. The Chinese rod numeral system was a huge deal, actively used from the 3rd all the way through the 17th centuries. It was a decimal system, meaning base 10, just like the one we use, but instead of drawing digits from 1 to 9, they used literal physical rods. And to clearly mark place value and make sure they didn't accidentally mix up columns next to each other, they brilliantly alternated the orientation of the rods. They used vertical rods, called zongs, for units, hundreds, and tens of thousands. And then they alternated those with horizontal rods, called hengs, for tens, thousands, and hundreds of thousands.
Now, you're probably wondering, why on earth would they need two different sets of symbols for the exact same numbers? Well, it's actually an absolutely genius method of visual chunking based on place value. When you write out a full number, you literally alternate between zongs and hengs. The zongs, the vertical guys, are strictly for the units place, the hundreds, the tens of thousands, and so on. The hengs, the horizontal ones, handle the tens, the thousands, and the hundreds of thousands. By bouncing back and forth between place values, the numbers stay beautifully organized and perfectly distinct from one another. It's basically a built-in formatting system.
We've got the rules down, so let's put that new decoder ring to the test. Our target number here is 2,634. I want you to try and visualize this in your head before we build it out. Remember, we're in a base 10 system, so think about those alternating zong and hong rules we just covered. We've got thousands, hundreds, tens, and units. Which shape goes where?
Okay, let's build this thing step by step, reading left to right. Step 1, the thousands place. It's a 2. Thousands use the hing symbols, so we lay down 2 horizontal lines. Step 2, the hundreds place, is a 6. Hundreds alternate back to zongs. Remember the rule for numbers over 5? Yep, 1 horizontal line on top, 1 vertical underneath. Step 3, the tens place is a 3. We switch back to hengs, so that's 3 horizontal lines. And finally, step 4, the units place is a 4. Back to zongs we go, drawing 4 simple vertical lines. Look at how seamlessly those horizontal and vertical rods slot together. There's literally zero visual ambiguity there. 2634 is perfectly clear.
So what exactly happens when a place value has absolutely nothing in it? I mean, how do you show 0 using physical sticks on a table? Well, much like the ancient Mesopotamian system, the rod numerals used a blank space. You just skip a spot. It works exactly like our modern digit 0. And let me tell you, this blank space is an absolutely crucial placeholder. Without it, all the numbers around that empty spot would just slide together and create a completely different, much smaller number. It'd be chaos. Now, you might be thinking, wait, isn't a blank space kind of easy to miss? But this is where the physical design of the system is just so clever, because the actual rods for numbers 1 through 9 were physically cut to be relatively uniform in size. Leaving a gap on the counting board created a very obvious recognizable visual break. Compared to other ancient written systems where the spacing could get super sloppy or irregular, this uniform blank space 0 was actually incredibly reliable. Okay, time to test those new code-breaking skills of yours. I've got a pop quiz question for you, pulled straight from our source material. Let's pretend for a second that these brilliant ancient mathematicians just forgot to invent the horizontal hang symbols. If you only had the vertical zong symbols to work with, how would you write the number 41? Try to picture it. 4 tens and 1 unit, stacked right next to each other. What massive problem is that going to cause?
If you just pictured a completely unreadable barcode in your head, you hit the nail on the head. Without that alternating trick, 41 requires 4 vertical zongs for the tens and 1 vertical zong for the units. Smash those together and it just looks like 5 vertical lines. I mean, is that a 5? Is it a 50? Is it 41? There's absolutely no way to know for sure if there isn't a clear, significant space between them.
And that perfectly illustrates why alternating between zongs and hangs wasn't just some aesthetic choice. It was a literal stroke of genius. It easily handles every required power of 10, it flawlessly separates adjacent numbers, and it completely wipes out any visual confusion. They took a literal pile of sticks and turned it into a high-functioning, robust decimal place value system. Just amazing.
So, here's a little practice challenge for you. I'm going to leave these numbers from the source material up on the screen. 63, 132, 200, and 360. I highly encourage you to pause this explainer for a second. Grab that pen and try converting these into raw numerals yourself. Just remember the golden rules. Start from the left, alternate your zongs and hangs, and whatever you do, don't forget the blank space rule for those zeros.
We just decoded a math system from thousands of years ago, but its core DNA, base 10, place values, the concept of 0, that is the exact same foundation that our entire modern digital world runs on today. So think about it. Where in your daily life do numbers play a crucial role? And how fundamentally different would our modern world actually be if ingenious place value systems and the placeholder 0 had never been invented at all?
Finally, we arrive at Section 5, the Indian number system.
So picture this. We're in ancient India, roughly 2,000 years ago. This is where the foundational structure of our modern oral and written numbers first originated. Scholars back then were conceptualizing math in ways that had literally never been done before, moving way beyond just physical counting objects. What is absolutely fascinating here is how ancient texts, like the Yajurveda Samhita, were already naming numbers based on powers of 10. And it's almost exactly how we say them out loud today. They had Eka for 1, Dasha for 10, Shata for 100. And get this, they didn't just stop at a few thousand. They explicitly listed names all the way up to 10 to the 12th power. They were already thinking on a massive exponential scale. Okay, if we contrast our everyday 10-digit system with Roman numerals, you'll immediately spot the game changer. The Indian system uses distinct, unique original symbols, which actually started as early Brahmi numerals, for the base digits, instead of just stacking lines on top of each other. Think about the Roman system. Counting to 3 means writing 3 separate I's. To write 8, you need a V and 3 I's. But the Hindu system, it gave us solitary, unique symbols for every single unit from 1 to 9, which eventually evolved into the exact shapes we use today. Let's actually deconstruct a number, say 375. Notice how beautifully it breaks down into hundreds, tens, and units. And that's all because of its foundational structure. The 3 isn't just a 3. Its physical position tells us it's 3 times 10 squared, so 300, and the 5 is just 5 times 1. By definition, this makes it a base 10 positional, or place value system. Essentially, the location of the digit completely dictates its mathematical worth. Because of this rule, only a single digit occupies each position, which completely eliminates any ambiguity when you're reading or writing massive numbers. It is just a beautifully elegant piece of logic. Now, to make a place value system work flawlessly without confusing everyone, humanity needed a massive breakthrough. And it is absolutely mind-blowing to realize that the very first time we see all 10 digits written together, with 0 appearing as just a simple dot, is in the Bakhshali manuscript from the 3rd century CE. Before this, if a place value column was empty, it could cause total chaos. That one little dot literally changed the trajectory of human history. But zero wasn't just some placeholder to keep the columns neat. No, mathematical giants in India completely transformed it. Around 499 CE, Aryabhata started explicitly using its arithmetic properties for really elaborate scientific computations. Then Brahmagupta came along and codified zero as an actual number, totally on par with 1, 2, or 9. By defining rules like 0 plus any number is that same number, he helped create what modern mathematicians call a ring. This directly laid the groundwork for modern algebra.
So, the actual structure of the modern numbers we speak and write today, that originated thousands of years ago in India. Ancient Indian texts, like the Yajurveda Samhita, already had these incredibly structured names for numbers based precisely on powers of 10. Let's solve 3 quick examples orally to hear how this translates. Question 1. Solving for 11. You would logically combine Eka for 1 and Dasha for 10. Simple. Question 2. 110. You combine Dasha for 10 and Shata for 100. And question 3, 1,100? That's Sheka and Sahasra, 100 and 1,000. They systematically named these powers all the way up to 10 to the power of 12 and beyond. They were orally structuring math exactly like we do right now, centuries before the modern digits we know were ever drawn.
So, from its birth in India roughly 2,000 years ago, this system went completely viral. By 800 CE, it had reached the Arab world where it was popularized by the great mathematician Al-Khwarizmi. Fun fact, his name is actually where we get the word algorithm. From there, it traveled to Europe around 1200 CE, championed by Fibonacci. And despite some intense resistance from folks who loved their Roman numerals, the Hindu system finally became the universal standard by the 17th century. Why? Because ignoring it was literally holding back scientific progress. When you really compare the two, it's pretty obvious why the Hindu numerals won out. Without zero, trying to do advanced scientific calculations or algebra with Roman numerals is, well, it's kind of like trying to run a modern smartphone on a dial-up modem. Roman numerals were totally fine for just recording numbers, but they were absolutely terrible for actually doing math with them. Okay. So you've absorbed all the history and mechanics. Now imagine we're standing right here at the chalkboard together, chalk in hand, ready to crack a few of these ancient computational problems. I want you to really think about the answers before I reveal them, okay? Here is your first quiz question. If you were a scholar in Europe before the Hindu system took over, how would you multiply the Roman numeral V by the Roman numeral L, using only Roman numerals, and no cheating? Don't just translate it into base 10 in your head. Try to do the actual math using just the letters. Got it? The answer is CCL. In our modern system, V is 5 and L is 50, so the product is 250. In Roman numerals, 250 is written as CCL. That's 2 hundreds, the C's, and a 50, the L. But just think for a second about how incredibly clunky it is to compute that without our trusty base 10 structure. There's literally no straightforward algorithm to just multiply a V and an L together. Let's try one more. How do you multiply 7 times 9 in Roman notation? So that's VII multiplied by IX. Again, try it without converting it to 7 times 9 first. The result is LXIV. That represents 63, an L for 50, an X for 10, and 3 I's for 3. Just looking at that clunky equation perfectly highlights the absolute genius and efficiency of the 10-digit Indian system we use today. We just memorize our times tables and use place value to multiply massive numbers in seconds. Now, consider this real-world scenario. How could early civilizations possibly handle massive arithmetic division, or balance the complex accounting of international trade using only physical tally marks or string-based names? Just imagine trying to physically divide 1,000 sticks by 27 sticks. The harsh reality is they couldn't. Not efficiently, anyway. Without the place value mechanics and the brilliant invention of zero as a standalone number, the advanced math required for modern engineering, accounting, and computer science would literally be impossible to perform. So, I'm going to leave you with this final thought to ponder. If ancient Indian mathematicians hadn't invented this precise base 10 system and embraced the magic of zero, would we even have the digital, scientific world we live in today? I mean, every piece of software, every skyscraper, every financial market relies completely on this ancient numerical breakthrough. So definitely keep that in mind the next time you type a simple zero.
I'll leave you with this provocative thought as we wrap up this explainer. If the entire foundation of human mathematics, architecture, and scientific progress was built on a base 10 system simply because of our physical biology,
How fundamentally different would the universe look today if human biology had handed us an 8-finger math system instead? Just think about it. Keep exploring, keep questioning, and I'll see you in the next explainer.